So both thanks to everyone for coming, and thanks for Joe for giving this presentation today. We're really excited for his talk. Um, this will be the last GeoDAWG seminar before we kind of take a little bit of break for the summer and all of the heavy conference travel we have coming up. So we're very excited for to Joe to close out the slate for us. Let me see if I can go. Yeah. So just a little bit of time for our normal announcements. A little less, I guess, checking the seminar schedule will be important coming into the fall. We'll start populating that throughout the summer, and we'll kind of try and pick up closer to September or so. So check after all your busy conference schedule, check back here, and we'll have some really nice talks going into the fall. There's also a good reminder to sign up for the mailing list because we will also send out reminders to that too. So if you forget to check the website, join the mailing list and you can jump on that. And then if you are missing GeoDAWG while you're on travel, we do upload all of our presentations to YouTube. So feel free to come back to our website and check on those. Each of the presentation names will be a URL link to the video recording on YouTube. So you can be able to watch all of those there. So I will now pass it off to Anthony, who's going to introduce Joe for today.
All right, thanks very much. Just a quick reminder to please keep yourself muted unless you're going to ask a question, but Joe is very happy to take questions today during his talk, so feel free to jump in and have a discussion on whatever you're interested in. Today we have Joe Hughes visiting us from Orion Space Solutions, which I believe is based in Colorado. He has a lot of experience in studying the ionosphere through many different methods, and is going to come today to talk to us about the relative merits of Ionosondes, ground TEC, and radio occultations for ionospheric data simulations. So thanks very much for coming to talk to us today, Joe, and feel free to take it away.
Awesome. Thanks so much. Let me get my slides up. All right. Can someone confirm that they see the slides in presentation mode?
I can't yet. It says that you started screen sharing, but I haven't seen the slides yet. All right. And of course, we just dry run this and it worked fine. So
yeah.
Can you see them in the regular mode?
The screen's still black. It looks like it's still trying to pull it up on screen share.
Okay, it worked just a second ago.
Yeah,
I guess it's. All right, we're going to try this again. Okay, is it sharing now?
Not yet. It's still the same screen. How are you sharing? I usually have success pulling PowerPoint up into full screen and then sharing just the full monitor that the.
Yeah, I am sharing the entire screen.
It's weird.
All right, let me try it a third time. This did work a moment ago.
It literally just went.
Yeah.
Okay, I am allegedly sharing the screen and haven't switched over.
Still don't see it yet.
Okay. Adam, we tried this before everyone joined. What do you think is different now?
Nothing's changed, so I'm not sure.
Maybe you might want to log in back or sign in back to Zoom just to see, or put the video up if that's something. Maybe you could do the video, like show your.
Oh, sure.
Yeah, maybe that might. Then maybe try share screen right now, so it's working, and then
Yeah.
let's do that. If it's not, then
If it's not, you can email it to one of us and we can drive.
Okay.
Okay. It says I'm now sharing the screen,
I
but
know.
I'm guessing you guys don't see anything yet.
No.
Okay, I'm gonna log out and back in. We'll try that. Sorry, guys.
All good.
Are there Zoom update these days?
All right. Can everyone hear me all right?
Sounds good.
Okay, awesome. Well, my name is Joe Hughes, and despite the technical difficulties, I believe we are up and running. So what I'm talking about today is the rather lengthy title of On the Relative Merits of Data from Ionosondes, Ground GNSS Receivers, and Radio Occultations for Ionospheric Data Assimilators. So I've organized this into 4 acts. So the first act we're calling the question. We're basically going to ask ourselves how impactful are different types of data. And then act 2 is going to be how we found the answer. And the answer to that is Aussies. We used Aussies to answer this question. And then in act 3, I'm going to tell you the answer to that question. And that answer is basically that different data are good for different things. And then in the 4th act, I'm calling this one the future. And this is sort of a chance for some audience participation. And the idea is I want to discuss the idea of this as a community data set and benchmark. All right, so with no further ado, let's start on Act 1. So the question is, how impactful are different types of data? So in this seminar series, I probably don't have to go too much into the basics of data assimilation, but humor me if you will, and let's just look at a simple example. So data assimilation is a way to update an incomplete model using sparse and imperfect measurements. You begin with a background, which we call XB here, or sometimes a forecast, depending on the nomenclature in your very precise field, and you combine those to produce an analysis, which we have over here. And this, of course, is the Kalman equation. And you can see a very simple example where you have a background. In blue, it's just a value of 0 everywhere with an uncertainty in that shaded area. And then you ingest one single data point in orange with error bars right here. And then your analysis will rise to meet that right here. And in this example, we have an uncertainty of 0.3 in the background and an uncertainty of 0.1 in the data. And the analysis moves 75% of the way to meet this measurement, which is, interestingly enough, the ratio of 0.1 over the sum total of the uncertainties. So this is what data assimilation does. And then one of the most important and perhaps some of the most undersold pieces of data assimilation is the covariance matrix and covariance models. So covariance drives almost everything. It's these P's and R matrices inside that govern the covariance that dictate the Kalman gain. And you can see how that shows up. So the P matrix describes how much you trust your background model. The R matrix describes how much you trust your data. And then R we assume is diagonal. We assume that the errors in the data are uncorrelated. And then P, we let those errors decay. The off diagonals, we let those be governed by the distance between those 2 points. So here are some 2 examples where we varied the uncertainty in the model, and you see that as the uncertainty drops, we go higher and higher closer to the data. And then as that uncertainty in the data grows, we revert more and more towards our background model. And then if you change the horizontal correlation length called L, it really governs how much we change the analysis far away from the data. So once again, this is probably old news to everyone on this call, but it's nice to give a little bit of background. So within the ionosphere specifically, there are 3 big data types for ionospheric data assimilation. The first one is ionosondes. Ionosondes record the time it takes for HF radiation to go up to the ionosphere, reflect, and then return to the ground. Now, this delay can be inverted using a bunch of different mathematical formulations to give you a profile of electron density with altitude for the bottom side of the ionosphere. Now, there are ways to do data assimilation which just use the HF, the actual delays, but we're not talking about those today. So that's data type number 1. Data type number 2 is ground GNSS TEC. So the GNSS satellites broadcast signals at multiple frequencies. You can, because the ionosphere is dispersive, the relative delay can be used to calculate the total electron content, or TEC, along the path. You kind of have some geometry here. So we've got an ionosonde in Africa that sends signals up, they bounce and they come back. And then for GNSS ground station TEC, you have a satellite, and then you measure sort of the line integral, the total electron content between these 2 points. And then for radio occultation, it's the same as GNSS TEC, but the receiver is on a satellite in low Earth orbit. And just to make it explicit, TEC is the line integral from the transmitter, which in this case is a GNSS receiver GNSS satellite, to a receiver, either in low Earth orbit or on the ground, of the electron density as a function of position multiplied by an incremental distance, ds. So it's a little bit different because the state that we're usually interested in is electron density. So you have to invert this equation. So how do we do that? Well, we can transform TEC into electron density using something called tomography. This is incidentally the same type of math that's used in a lot of medical imaging equipment. And in data assimilation, this is done in what's called the observation matrix H. So earlier we had this line integral for TEC. We can break this into a little bunch of pieces. So we have the finite sum from the transmitter to the receiver, the electron density times a finite but small distance in the ionosphere. And then if you have a bunch of these measurements right next to each other, well, you can write this as a matrix equation. So you have TEC from the first measurement is going to be all its different distances, and then all the different electron densities. And then you can stack those up and you can get a big matrix equation where you get TEC equals H times electron density. So that's that H matrix. Now, it's important to note here that TEC can be used in an absolute sense, or it can be used relative to an anchor measurement. And what we mean by an anchor measurement is that you basically say, this geometry is sort of our baseline, and you're going to look at changes in the TEC relative to that initial anchor point. So, okay, with all that out of the way, now let's get on to what this talk will mostly be about, which is trying to build some intuition for what these big 3 sets of data are going to be good for. So ground GNSS TEC has primarily vertical line integrals. So you're mostly on the ground looking straight up. And of course, you can get some low elevation measurements, but it's primarily a vertical measurement. And radio occultation has primarily horizontal line integrals. So we should be able to resolve vertical structures with RO and horizontal structures with ground TEC. And I'm going to walk through some pictures as to why I think that. So in this first one, you'll see we have a grid of yellow and red squares. Is basically the simplest ionosphere that you can imagine. Red means high density, yellow means low density. And you'll see that if you have 2 ground receivers here and here, and they're both looking up, they're going to see the same TEC measurement because they go through one yellow square and one red square. So in this case, the ionosphere is a vertical structure, but the ground GNSS measurements are not sensitive to it at all. You can't even tell that there is a difference, let alone what that difference is. So that's our first example. And our second example, we are putting a horizontal structure in the ionosphere. And now you can see that T1, since it goes through 2 red squares, is higher than T2, which goes through 2 yellow squares. So in this case, we are sensitive to horizontal structure with our ground GNSS measurement. Now let's switch to radio occultation. So with radio occultation, the lines are primarily horizontal. And you see both of these line integrals go through 1 yellow and 1 red square. And so we can see that radio occultation is not sensitive to the horizontal gradient because T1 equals T2 here. But then finally, let's go back to our vertical gradient example. And we can see that T1 is greater than T2 because we go through 2 reds rather than 2 yellows. So all of this put together should say that you should be able to resolve vertical structure with RO and horizontal structure with ground TEC. This shouldn't be all that surprising, but it's still nice to write it out explicitly. So that's the theory. And then we have one corollary to theory. And that is that combining radio occultation and ground TEC should allow you to resolve both vertical and horizontal structures at the same time. And put another way, we should say that the whole of RO and ground TEC should be greater than the sum of its parts. So in this example, we have a bunch of yellows and oranges and reds And if we have all 4 of these line integrals, we should be able to invert this system and find the electron density everywhere. So based on all this, I wrote down 3 hypotheses. So the first hypothesis is, does RO help specify vertical structure? The second one is, does ground GNSS TEC help specify horizontal structure? And the third hypothesis is, does the combination of RO and ground GNSS TEC specify the ionosphere more than either of them in isolation? So basically, is the whole greater than the sum of its parts? And my suspicion for all 3 of these is yes. I think it's true for all 3 of those, but that's what we're going to test in this talk. Okay, so that was Act 1. That was the question, and we ended up with 3 hypotheses. Now for Act 2, we're going to look into how we found the answer, and the answer to how we did this is Aussies. So for those of you who haven't met me before, you may or may not be familiar with Aussies. It's something I talk about far more than I really ought to, because I get really excited about them. So an Aussie is a numerical experiment that can answer what-if questions just like the ones we posed. So it's an acronym. It stands for Observing System Simulation Experiment. There's 3 steps in it. The first thing you do is you simulate measurements from a truth model. So here we've got a bunch of white dots that sample this truth model, and I'm showing FOF2 here. And then we assimilate these measurements. You add some errors to these measurements, and then you assimilate them along with a background model to make an analysis. And now what you can do, you'll notice, and I'll point just to Hawaii. So Hawaii was purple in the background, and then we sampled it, and it was sort of this orangey yellow color. And we did update it right there in our analysis. But other places where we didn't measure did not get updated. And so here, what we just did is a visual comparison, but you can do a more detailed comparison if you'd like, since you have full 4-dimensional electron densities, that's latitude, longitude, altitude, and time for the truth and the analysis after the fact. And then you can iterate on steps 1 through 3 with different types of different configurations of the observation system. So this could mean the assimilator, this could mean the data types, this could mean the pre-processing, and you can choose one that best meets the need for whatever you're trying to do at the minimum cost. My company has developed something called the Aussie tool, or OSSIT, that can sort of orchestrate this entire process and do it quickly and robustly. And we are, I believe, close to publishing a paper on this very topic. So one of the big aspects in an Aussie is the truth model. And we're going to talk about why that matters. So have sort of an example here. This upper left picture should look very familiar. It's what we talked about initially as the foundations of data assimilation. And this is what would happen if rather than just giving one measurement, we're showing up a magenta line that shows what the truth is, even though we only measure it in one place. So if this is your situation, you get an improvement, and we basically said the improvement is the area under this curve of 40%. So we made things better by doing this. And this is what happens if the truth is smooth, just like the background. But now let's take an example where the truth is noisy. So rather than a steady state value of 2 for the truth, now it's a sine wave. And you'll notice that this truth is on average the same as in the smooth case. And the measurement is also the same. So the analysis doesn't know any better. It does exactly the same thing because it's just being given this one measurement. But you can see that not only is the mean improvement a little bit lower, it's 30%. There's actually at least one place right here where you make things worse rather than better. So in the smooth case, the average improvement is 40%, while in the noisy case, it's about 30, and in some places it's worse. So based on this, we say that a truth model that is smoother than reality can give erroneously optimistic predictions. So given that, you might wonder to yourself, are our truth models too smooth? And the answer is yes. So this curve shows a time history of FOF2. The orange curve shows a smooth truth model that's often used for Aussies. And then this blue one shows real data from an ionosonde. And you'll notice that it is far jumpier than the truth model would have you believe. And then additionally, if you take a whole year of this and use Welch's periodogram to take the Fourier transform, you can see the power spectra in here. So the Ionosonde data in blue has a lot more power, especially at low frequencies. So at 10-minute frequencies, we have probably 2 orders of magnitude difference between these two. So in order to fix this, we came up with a solution called the noisy truth model. What it is it's a realistic truth model built from TiGCM plus structured noise. So this This noise we added is spatially and temporally correlated. We used 2 years of Ionosonde data to do this, and the noise is specified by amplitude, horizontal correlation length, vertical correlation length, and temporal correlation length. And each of these parameters vary with altitude, season, solar activity, and time. So here's an example right here. This is at 150 kilometers, and you'll see that TIE-GCM in the top panel is primarily solar zenith angle driven. So this kind of looks like a little excerpt of a rainbow or an upside down rainbow with these smooth arcs varying with solar zenith angle. And what we did is we added temporally, spatially correlated noise, and we get the panel on the bottom. So this is what we think the ionosphere actually looks like. You'll notice that it is lighter in color in the upper left than the lower right. So it's similar to that, but we have a lot of small scale structure that we've introduced into this. Now, I want to be clear that we're not claiming that there is actually an enhancement right here. We just think that the enhancements and depletions are going to be about this size, and they're going to have they're going to last about as long as they would if you were looking at a video of this. And here's the paper on that if you want to read more about it. Okay, so now that we've talked a little bit about Aussies, let's get back to our main hypothesis. So our main hypothesis dealt with what different types of data were good for different types of things. So what we did is we used the noisy truth model and OSSIT to simulate data from Ionosondes, ground GNSS TEC, and radio occultations. So we simulated all 3 of these data sets. And then what we're going to do is we're going to simulate all unique permutations of this data in separate assimilation runs. So there are 2 times 2 times 3 minus 1 options for how to do this. So you can either have yes or no on Ionosonde data, so that's 2. And then you can have yes or no on ground or on radio occultations, that's another 2. And then you can have no, yes in absolute, and yes in relative for ground GNSS TEC. So you have 3 options for that one. And there's 1 option, which is a no, no, no. So we subtract that one off because it's kind of a null case of no data. So we have 11 different assimilation runs, and we've got this nice little table here. So we have the run number, it goes 1 to 11. And then the name is this sort of code that you can probably crack reasonably easily yourself that tells you what data went into it. So just a capital I means it had Ionosonde data and nothing else. This IG little r means it had Ionosonde data, no RO, and then relative ground GNSS TEC. And I'll stop here and remind people that we can assimilate TEC measurements either in absolute sense or relative to some anchor measurement. So that's what this is related to. And we only have this for radio occultations, we only do it in a relative sense. And for ground GNSS TEC, we can do it either way. So these are all the codes. So a capital I means Ionosonde data was used, a capital R means radio occultation was used, and then capital G means we used ground TEC, and the little r afterwards means it was relative, and the little a means it was absolute. Okay, so we simulated all this data, and then we're doing 11 separate assimilation runs, which have different permutations of the data ingested. And then what we're going to do is we're going to rack and stack and compare the performance of each of these analyses to each other to confirm or deny our 3 hypotheses. So let's talk a little bit more about our data. First, I want to introduce this lovely figure that one of my collaborators, Ian Collett, came up with. And this, we call these fan plots. So the basic idea is that ionosondes measure really things in one place, and it's easy to understand. The ray goes straight up, it goes straight down, and it's easy to understand. But TEC measurements are very widely distributed. So if you think about a ground GNSS satellite, it's actually measuring things all the way between the GNSS receiver and the GPS satellite. So this ray goes through a bunch of different altitudes, and we're going to use color to explore that. And then for radio occultation, it's even worse because this ray is primarily horizontal, so it goes all sorts of places over the globe. And so if you look at the ray in this example, it starts off at the cosmic satellite, then it's going to descend a little bit. We're going to say 500 kilometers is red, and then it descends a little more. It goes to this gray area around 300 kilometers, and it's going to go all the way down to the lower ionosphere around 100 kilometers. It's going to stay there. And it's going to climb up again through the ionosphere again, go through the F layer at 300 kilometers, and then exit the ionosphere at 500 kilometers over here, and then keep ascending all the way to the GNSS satellite. And so for radio occultations, we can look at this plot down in the lower left, and you'll notice that there are white lines that show the orbits of the Cosmic 2 satellites at this time. And then each ray is sort of shown with this color. And you can see like some examples where you'll have the ray that goes from, like right over here, you have one that starts with red and then it descends, gets that gray color and then that blue color, and then it climbs out of the ionosphere again and is red again. So this just shows around 15 minutes of time, the type of data that comes in from the Cosmic 2 constellation. So this is a nice way to visualize that data. And then our ground segment is shown in the right panel, and you can see that all of these plots pretty much just go from blue to gray to red because they're primarily vertical measurements. They don't have anywhere near the horizontal extent of the Cosmic 2. And then we have green triangles for our Ionosondes. So all together, we have 47 Ionosondes, 262 ground GNSS stations, and then all 6 Cosmic 2 satellites. So that's a little preview of our data that we ingested. Now I'll talk a little bit about our assimilator. For this work, we used the recently developed Modern Modular Model for Space Data Assimilation, or M3SDA, which we pronounce Mazda, like the car manufacturer. Now Mazda has a bunch of different modes and configurations. In this case, we used an extended Kalman filter to do this work, or EKF. And then Mazda also cycles the covariance in state, and we have a little diagram of this that you probably can't read down at the bottom, but basically we used prior history to change the background a little bit to get away from persistent errors. So as I mentioned before, covariance is a really big deal, and it dictates pretty much everything that your data assimilation will do. So the data variance is 35% for all 3 data types. We assume that the data errors are uncorrelated so that our matrix is diagonal. We actually never form the full 2-dimensional matrix. We only do the diagonal. And then the model variance is 50% everywhere. So that means that that's the uncertainty in our background. The horizontal correlation length for this, we set at just 7 degrees everywhere. And the vertical correlation length is 1/6 the altitude at any place. We use the IRI model as our background, and we computed this with Pi IRI, which made our lives much easier. So I want to thank Victoria publicly for releasing that. And then our grid is a global 4x4 degrees. Vertical resolution is 5 kilometers in the ionosphere. And then we bump that resolution up as we get higher up, because with TEC measurements, you want to have your grid go all the way up to GPS altitude. So we make it all the way from 100 kilometers to 20,000 kilometers, but our resolution increases drastically once you get outside the ionosphere. And a time step is 15 minutes. So that's the basics of our assimilator. And now I want to talk through some, in my opinion, these are really fun plots, but they require a lot of explanation. So let's jump into it. So what we did is we turned our state into plasma frequency. So we went from electron density to plasma frequency, and we subtracted the background from the truth and then each of our 11 runs. Now the top panel basically shows histograms of what that difference is. So let's start at 150 kilometers, so the blue line, and you'll see that right here, the x-axis is the truth plasma frequency minus the background plasma frequency in megahertz. And you'll see that the difference is basically zero mean, that it goes off the chart right here, and it extends a little bit to the positive side. And so there's not a huge bias between the two. But at 350 kilometers, we're looking at this orange line. The truth is often lower than the background. So up in the middle F region, the truth is lower than the background. And that means that we have a negative bias here. So this orange curve is shifted to the left. And then at 550 kilometers, so now we're on the top side, this green line is shifted to the right. So that means that the truth is higher than the background. So the histogram of this skews positive. So this is just 3 altitudes, 150, 350, and 550. What we want to do is we want to explore that for all altitudes. So if you can imagine taking each of these different histograms and then shifting them vertically and stacking them up along the y-axis, you'd get this plot right here. So once again, you've got the blue line just sort of reminding us where 150 kilometers is, and the increases in opacity in this black curve show us where each curve rises and gets above one of the tick marks on this y-axis. So just to follow along, let's pick the orange curve. We go above 1 in normalized counts right around here at around -3 megahertz, and that's incidentally, that is where we get our first increase in opacity. And then up here we cross 2 right around where my mouse is, and you'll see that that's where we increase opacity again, and we decrease it right there. And so you can kind of follow along with each of these. And so this is a really nice way to look at how different the truth is from the background at a bunch of different altitudes. And the thing that I want to notice is that the analysis needs to, so the truth and the background differ not that much at low altitudes, but in the F region, the analysis needs to decrease in order to match the truth. And then on the top side, it needs to increase. So these are this is what we're working with. And this histogram shows how different the truth and the background are from each other. The next slide will show how the analyses do. So this is looking at just the truth versus background. Now we're going to look at the analysis and background. So this is the same type of plot, but rather than, now we've got all the different analyses. Now, I said there was 11. Now we're only looking at 5 right now. So what happened? Well, I'm not showing anything that has Ionosonde data in it, because the Ionosonde data does not change much, does not change these global stats very much, because there's just not that much Ionosonde data, sadly. So this is really interesting to me. One thing I want to point out is two of these look different than the rest, right? So you've got this blue one and this purple one that look very different. And all the other ones, the green, the purple, the yellow, they have this sort of belly that bows out to the left around 300 kilometers. So they are getting closer to making the necessary decrease in the F region in order to match the truth a little bit more. So if you can think really briefly, kind of remember our hypotheses, some of these analyses have more vertical structure than others. And what do we think these have in common? So if you look down to the x-axis, you can see the codes for the names. So this blue one is GR, this pink one is GA, and then all the other ones have an R somewhere in the name. So all the ones that are getting close to decreasing the F region electron densities have radio occultations in them. So this is a hint of where we're going for our 3 hypotheses. Okay, so that was a teaser for how we found the answer. Remember in Act 2, we talked about Aussies, we talked about the noisy truth model, and then we talked about all of our assimilation runs, and then we did a little bit of visualization of how much that data changes the analysis. So now we're going to talk about the errors. So this slide here shows the TEC errors at 3 universal time in TECU. And this is a little different from the last slide, because the last slide showed how much each analysis changed, but it didn't actually talk about whether that change was for better or for worse. And we could kind of get that by comparing to that black colored contour histogram on the left side, but now we're doing it explicitly. So what we've done is we've created the errors in vertical TEC, FOF2, and HMF2, and we computed them for all of our models. So we've got the background up in the upper left, and then all our 11 runs in the preceding panels. Now we're going to use VTEC as a measure of horizontal structure, and then we're going to use FOF2 and HMF2 as proxies of vertical structure. So let's return to this plot. The background here over predicts the TEC in the tropics, but under predicts it at high latitudes. So we see some blue in the northern US and Canada, we see some blue in Antarctica, and then we see some red right around the tropics here. So we're over predicting by sometimes as much as 8 TECU. So that's what we're dealing with initially. And then different types of data solve this to more or less a large or smaller degree. So you can see the Ionosondes, there's just not that many of them. And some places like the US, we get closer to this sort of light yellow color. Hawaii specifically gets a little better. And then different other types of data manage to get things better. So some things I'll point out is that radio occultations are primarily in the tropics because we're using Cosmic 2. So those don't really change things at high latitudes. And then GAs and GRs, so that's the ground-based tech, those are primarily over the continent. So you're not going to get much data over the ocean. So you can stare at this for a while and kind of come up with trends. But I think it's actually easiest if you can sort of squint, maybe tilt your head back to the side, and then just see rows and columns, which ones are best. So some of these analyses correct the horizontal structure more than others. And what do those have in common? So if you look at just one row at a time, you'll notice that the bottom row, those 4 analyses down there have an awful lot of those low errors. So the colors that are sort of these soft yellows. And what those all have in common is that they used the GA data set. So this is getting, once again, close to our 3 hypotheses. So that was a nice plot of the errors at all places. It was a map, and then one time. What we want to do is we want to combine the errors at all places and all times into a single histogram. And then we want to do this for each of our 12 cases because we have one background in 11 analyses. So to do that, we're going to use the method here. So this is just showing it for one run. I happen to use the IGA, so that's going to be Ionosondes and absolute ground tech. And you'll notice the distribution of the errors in the background is shown in gray up top. And you'll notice that the VTech error extends really positive for some cases and then really negative for others. It has a tiny bit of a bias. And then once you assimilate data, you get this curve down here in the blue, and it is far narrower, far pointier, and it's got much less bias. So this is good. We've managed to move a lot of our errors from the far field into the near field, and the VTech error decreased pretty much everywhere. So this is a tighter distribution. This is less bias. So this narrow distribution is good. We've done well here. So this is really just an intro to our next plot, which is going to show this for all of our 12 cases, and then for all of our 3 metrics, which is the vertical tech error, HMF2 error, and FOF2 error. So this is a monster of a plot. We're going to be talking about it for a while. So I'm going to give us a rundown of how to read it. So each shape on this plot is a histogram just like the earlier one, but it's rotated by 90 degrees. And you'll notice that each of these histograms is actually 2 histograms. So there's pairs. So in each of these pairs, the one to the right ingested Ionosonde data. And as I've mentioned a few times so far, there isn't much Ionosonde data, so it doesn't make a huge difference in global stats like this. And it's actually easiest to see its effect if you compare it to something that's very much like it but didn't have Ionosonde data. So for example, we can see that there's a difference in FOF2 with the ground relative tech. We can see that it looks like there is a shift lower in this case right here, whereas other cases it's not as obvious. So that's what the pairs are. And then another thing is that we've limited this analysis to latitudes equatorward of 40 degrees so that we better overlap with cosmic 2 radio occultation measurements. And it's easiest to understand that. Okay, so this is how you read the plot. And then I guess once again, just to speak to this, both the colors with the label and the x-axis ticks show the data that was ingested. So in this plot, the magenta and the black show the background and just Ionosonde data. And then this next one shows just ground relative tech in the blue and orange with or without Ionosondes. The next one is radio occultations and ground tech, and then just radio occultations, and then just absolute ground tech, and then radio occultations and absolute ground tech. And then each of the 3 vertical panels are the vertical tech, HMF2, and FOF2. So there's a lot of info in this plot. Let's step through it one at a time. So now I want to just look at the top panel and show that 2 of these families of analyses do way better than the others. So remember, we want a pointy distribution that is centered at 0, where we have this handy black line to show us where that is. And you'll notice that these 2 families of analyses do really, really well in this case. And what do they have in common? Well, they have absolute ground tech ingested. So this should not be too much of a surprise. Vertical tech is very similar to absolute ground tech, so it would make sense that you do really well if you assimilate that measurement, because it's a really one-to-one or direct correspondence there. So that's our first finding, is that absolute ground tech helps to specify VTech. Our second one is that radio occultation data helps to specify HMF2. So if we look at just this middle panel, we'll see that our initial background had a bias. If we add relative ground tech, it doesn't really go away. But if we add radio occultations or and ground tech, so either of these two, we've really reduced our bias. We haven't eliminated it, but it got a lot better. So we've managed to take this peak and drop it down pretty low, which is excellent. And then our third finding from the lower panel is that RO data also helps to specify FOF2. So if we look at FOF2, we're pretty bad to begin with. Relative ground tech helps a little bit, but when we add RO to that, we managed to get really, really good. Once again, we haven't completely removed the bias, but we've done pretty well. And then this will be important later. But if you look at radio occultation, the peak of this distribution is very, very close to 0. And then if you look at radio occultation and absolute ground tech, that peak rises up a little bit again. So this is a bit of foreshadowing, but this is a situation where we have added data to radio occultations and things have gotten worse, not better. So I'm just going to leave that as foreshadowing for now, and we'll return to it later. So our fourth finding is that relative ground tech does not add much to RO. So if you look at RO, which is just this brown and purple distributions, you say, okay, it's doing pretty good. And then you say, what happens if we additionally give relative ground tech to this? And the shapes of the distributions are slightly different, but they're very similar. So it's basically, once you have RO, relative ground tech does not really help you that much in any of these stats. You don't get much better. You don't get much worse. It's almost like you didn't add it at all. But if you add, instead of relative ground tech, if you add absolute ground tech, you get VTech performance. So you get this really nice narrow distribution here. And then the HMF2 changes a tiny bit, but not very much. And the FOF2 actually gets a little bit worse. So by adding absolute ground tech, you've managed to improve your performance in VTech, but at the small cost of a little bit of FOF2 performance. Okay, so given all of that, let's revisit our three hypotheses. So hypothesis 1 was about vertical structure and RO. So our proxy of vertical structure, which is FOF2 and HMF2 errors, does improve with the addition of RO data. So if you give RO data to either of these, and pretty much in any combinations, you do much better with vertical structure. This was fairly intuitive, but it's nice to see it borne out in experiment. So that's our first hypothesis. That's a check mark. That's a yes. Our second hypothesis was about horizontal structure. So our proxy of horizontal structure, which is VTech, does improve with the addition of ground GNSS TEC. And that's especially true if we ingest it in absolute. So in absolute, we get these beautiful narrow distributions. They kind of look like witches' hats to me, rotated sideways. So this is also a yes. So we give absolute ground tech. We do really well with horizontal structure. So now let's go to hypothesis 3. And that one is basically that the whole of RO and ground GNSS TEC should be greater than the sum of its parts. And we find that to not be true. So this is an X rather than a check mark. So radio occultation and ground GNSS TEC does not surpass the performance of either one on all three metrics. So, and the reason we say that is when you give absolute ground tech to RO, we actually do a little bit worse in FOF2 errors instead of better. We do manage to do much better at VTech, but it's at the cost of doing a little bit worse at FOF2. So for our three hypotheses, we got a yes, and a no. Now, while we're doing this, let's also talk about two surprises we found when doing this. So the first one is a bit of a maxim that the more data you give a data assimilation system, the better you think it ought to do. And that is sometimes true, but sometimes false. So, and I'll bring up this once again using RO as sort of the baseline and then adding different types of ground tech. So when we add relative ground tech to RO, it really doesn't change much at all in these metrics. And when we add GA to RO, it makes VTech better, but it makes FOF2 a little bit worse. So that is a bit of a surprise that when you add data, it doesn't always get better all the time. Our second surprise is that there's no one combination of data that's the best for all three of our simple metrics. So if you want to do really well in VTech, you want something with GA, and it doesn't really matter what else you do. So you want one of these two on the far right. If you want to do really well at HMF2, you want anything with RO. So you want one of these three. And you do have one in common at this point. But if you want to do well at FOF2, you want to have RGR or R. So it's one of these two. So you actually don't have a good option to pick one set of data to do well at all three of these metrics. You have to make a choice and say, I care about HMF2, or I care about VTech, or I care about FOF2. And then you can make those choices. So that is also a bit of a surprise. Okay, so in all of this, it's very confusing, and you might wonder, why is it so hard to match FOF2 and VTech at the same time? So we did a case study to figure that out. So it's difficult to relate the previous histograms to sort of a real life, one time step, one place, electron density profile. So we wanted to do a case study here. And I'll mention that this is an example from Greenland, and Greenland is high latitude, so it actually did not make it into the histograms I just showed you, but it's just such a nice example that I had to use it, even though it wasn't as clean as using one that actually made it into those histograms. And part of the reason that it's so simple is that in our case, there are no Ionosondes or RO data in Greenland. So you're just dealing with ground GNSS TEC. So let's look at some EDPs. So in this right plot, we have a background in black, and you'll see that right here, it looks like NMF2 is around a little bit more than 2 times 10 to the 11. It happens around 250 kilometers. And then our truth is in magenta. And you notice that the truth has an aurora. It's a pretty strong aurora. It's almost higher than NMF2, and it peaks at around maybe 130, 140 kilometers. So the truth TEC is around 9.5 TEC-U, primarily because of this aurora, and the background TEC is around 4.7, 4.8 TEC-U. So when the analysis just gets the fact that there's vertically, that the TEC is much higher, what does it do? It increases everything, and that primarily happens in the F region. So both of these analyses, the orange and the blue, increase their TEC to match, and you'll see GA especially got to 9.28, which is very close to the truth. So this analysis thinks it's doing a great job because it's like, I match the measurements, I'm doing good. It has no reason to know that it's actually made things a lot worse because it doesn't know about this aurora. So it has increased the FOF2. It's overshot it by kind of a ridiculous amount, but it's matched VTech. So this is an example of why it's hard to match FOF2 and VTech at the same time. And the sort of the logic there is that if we don't know the vertical structure of the ionosphere, we don't have a good understanding of where to put the extra electron density, and because of that, we can get sort of bad. We can hurt the performance in stats like FOF2 and HMF2. So that's a short case study as to why this is. Okay, so that was acts 1, 2, and 3. So in the first act, we talked about the question. We had this sort of these yellow and red boxes that gave us an intuition for when we should be able to resolve vertical structure and horizontal structure. And our question was, what data are good for different things? And then we talked about Aussies, and we talked about how we had 11 different runs with different permutations of data. And then in Act 3, we actually looked at that data, and we had that sort of monster histogram with all 12 analyses and 3 different metrics, and we divvied this up into all 3 of these things and asked and answered our 3 hypotheses. And now I'm going to move to Act 4, which is the future. So I want to talk about a community benchmark and data set. So there are so many knobs to tune in the work I just presented. So the first question you might ask is, what would happen if you used a different horizontal correlation length? We used just 7 degrees everywhere. What if that was different? And what if we had one where it was 7 degrees on the day side and maybe 3 degrees on the night side? So there's valid questions about would these results still hold up in that situation. Another good question is, what about a different vertical correlation length? Well, how about if we decrease the measurement uncertainty? We use 35%. What would happen if it was 10%? Maybe what if we used a different algorithm rather than the EKF? What if we used 3D VAR or an ensemble Kalman filter? What if we used a different background rather than IRI? What if we used a whole different assimilator? You know, we've used Mazda here. What if we did your favorite assimilator? And I bet you probably have a bunch of other what if questions. And because I cannot do all of this work myself, I'm asking for your help. So I am planning to release the truth model that I talked about here, all the simulated data, and all 11 analyses with an upcoming paper. Now, why am I doing this? Oh, actually, so preview of this data. As I mentioned, there's 3 data types. We've got Ionoson data. There are 43,000 .NET CDF files. They've got the station name and the time and the file name. And each file is one electron density profile. It has a few variables. Not all of these variables are used. And then the RO data, we've got around 8,000 pod TC2 files, and they're exactly like Cosmic 2 provides. And the only change is that we've deleted the TEC values that Cosmic 2 gave, and we've replaced them with the TEC values that we simulate from our truth model. And then with ground GNSS TEC, we've got 262 net CDF files with station name and 1 file per station. And then we have a bunch of variables, some of which are used and some of which are not. So my ask of you is, first, let's go back and talk about all the data, and let's think about what I could do as I release this data to make this data easier to access. And then another thing is the covariance model. I think I've made it simple enough that I can explain it with just 4 numbers, and I have those numbers on the slide. Because of this, I wasn't planning on giving a file, but I want to make sure that it's easy to reproduce these results. And my second ask of you is, once this data is released, I'm hoping that you can take this data and surpass the results that I just presented. So I've got sort of a cartoon down here. This is my HMF2 error stat. And what I'd love to see is, over the next months and years, the whole community could use these results and use these metrics, and basically please show up what I've done here. So, you know, this dashed black line could be you. You could have something that manages to completely knock it out of the park with what I've done here. So if we all use the same data and the same truth model, it'll allow us to compare our approaches directly. So you could easily say, in an apples to apples sense, this is how much better one approach is than another. And it would be very easy to sort of compare performance. So this could be a community benchmark. I will be doing this with 3D VAR very soon. So this is a result with EKF. I am hoping to surpass these EKF results with 3D VAR very, very soon. And I'm very excited to see, you know, with everyone on the call, I think there's a huge wealth of different and interesting ideas as to how to do data assimilation with different assimilators, different everything else. And so I would really love to see these results become, you know, embarrassingly outdated very quickly. So please take these results and surpass them. So yeah, all in all, what we talked about was a question. So we looked at how impactful are different types of data. Act 2 is how we found the answers. So we talked about Aussies. Act 3, we found that different data are good for different things. And then my last thing is an ask for you to please provide some feedback on this data set and benchmark, and then take the results and go run with them. So I think what I'd like to do now is to, I guess, go back to some of these slides, and please tell me what you think of this data and how I can change it to make it more useful and easy for you guys to use in your data simulators.
All right, thank you very much, Joe, for a really great talk. Do we have any questions?
Can I go first? Possible?
Mm-hmm.
Yeah, please.
Awesome talk, Joe. Just bravo.
Oh, thank you. Thank you so much.
Yes, absolutely excellent. Yes, so okay, let me start with the questions. What I would also like to see in this kind of bake-off setting is the comparison of the thicknesses of the profiles. So F region top and bottom thicknesses, maybe to the histogram.
Oh, so so we don't do we do full electron density profiles.
Yeah, I understand, but you can easily derive the thickness from it. And
Okay.
it just would be a good and kind of good benchmark, I guess, to compare whether not only the main anchor points are improving, but also kind of the structure of the bottom side, because I think the bottom side F2 thickness is the second important parameter after your critical frequency.
Yeah.
Mm-hmm.
So here's maybe you could do, and I'd have to look for, I'd have to go and remind myself what the Epstein function looks like, but maybe you could do how many kilometers it takes for the frequency to go to half of FOF2 or something like that. Like that might be.
Yeah, we can do that. Or we can collaborate. I can kind of process your file and derive the thickness file. Yeah. And okay, and about those things, can you do it as simple as possible? For example, for GNSS case, can it be just XYZs of positions and the tech, and that's it? We don't need anything else, and the time.
Yeah. So your vote is, so these variables right here, tech data, sigma, fit error, signal strength, loss of lock, all this stuff is just sort of what it comes out of our pipeline.
Mm-hmm.
But your vote is to remove everything that could be confusing, right?
I think so. And also I vote for combining all of the data in one file. For example, not to have 262 files, but have like a pickle or netcdf output where it's the whole day, all data together with very simple structure, like time, position, tech, that's it. Because like for me, it's additional effort, to write this data aggregator for those types of files, and it would be very simple if it's all together.
Okay. So
I don't know what other people think, but I just.
No, this is great, and I'm hoping. I know that it took me so long to get my slides working at the beginning of the day, so I don't have a ton of time. But yeah, what do other people think on this? I was really hoping that this is where the discussion would go. And I can't see who else is on, so I can't pick on people who also have data assimilators running. But maybe, Victoria, you can help me, and you can pick on someone for me.
Well, Joe, this is Rutger Scheres. I think this is very great. We need something along this line, and definitely a very good start. I think eventually we need to move towards real data, to do this. But OSSIES is always a good start to see how things are going. I think your data files look good to me. I see XYZ position. Is that the ground and the satellite positions? We need both of those.
That's right. Yeah. So the XYZ are for the satellites, and then it's actually attributes for the ground stations because it doesn't change with time. So it's a little lighter of a lift, but I've written that down.
Perfect. Yeah. And my other question is, so you also make the truth data set then available, or?
Yeah. So I was planning on, so the truth model, that's a single netcdf file. It's a 4-dimensional grid, so latitude, longitude, altitude, and time. And then the simulated data, which is on the next slide. And then I was actually kind of going either way on all of my 11 analyses, mostly because it's just the data set gets to be a few gig, I think over 10 gigs, which is kind of a pain in the butt to move around and whatnot. But I think it might be nice just so that people, if I do actually want people to make a plot like this, I think I have to give them my analyses as well. But that was the plan.
Wait, one more question. I'm not sure if I got that right, but I think you use TIGCM to create the truth data, and then you add noise on it. Is that correct?
Mm-hmm.
So with that, your TC, probably your integrator stops at 500, 600 kilometer altitude. The upper,
very good question.
Of TIGCM, or what do you do with the plasma sphere?
That's a very good question, and I did not actually say that, so I'm glad that you brought it up. So as you mentioned, TIGCM does not go all the way to GPS altitudes. What we do is we we kind of have our vertical profile in 3 steps. So we go actually up to 400 kilometers with the noisy truth model. And then from 400 to, and then, well, okay. So the bottom half is just TiGCM plus noise. And then above 2000 kilometers, we default to IRI. And then in the middle, we actually just do exponential decay from there. So we take the electron density at 400, we take the electron density at 2000, and then we just fit exponential decay between those 2 points. And that's how we stitch our profile together in 3 pieces. So it's a little weird. And there's actually a few, like a handful of profiles where the exponential decay doesn't look quite right. So you do have some corners in the distribution, but since you're line integrating through them, it's not a huge issue. And that was just sort of the minimum error path to get through it.
Okay. Well, thanks. Great talk, Joe.
Oh, thank you so much.
Here is Sergey Friedman from Northwest Research.
Sergey, you're a little bit quiet. If you can get closer to the mic, maybe.
You cannot hear me?
It's a little bit
I
better
can hear
now.
you all right now.
Okay. Yeah, great talk. Thank you. And it's a good start. I agree with the previous comments. And of course, there are some ways to go. If we are talking about simulating operation with real data, then say for real, you don't have TEC measurements or VTEC measurements normally. I mean, with the few exceptions of special campaigns like JSON satellite. And this TEC, whatever TEC related measurements we have, they inevitably contain biases. And these biases are quite considerable, especially talking about absolute TEC. So I guess this thing eventually needs to be added to the simulation of the data. Do you plan on this? What do you think about
Yeah,
that?
that's a really good question. So right now we're maybe overselling the value of absolute TEC because we assume that we know these biases perfectly.
Yeah.
We actually have not added errors to the data set in any way. Normally when we do Aussies, we add characteristic errors, but we haven't, for this one, we've just made it as easy as possible and not done that at all. So that would be actually a really important caveat, is that we're probably overselling the value of absolute TEC here. But I feel like it's in the, there are many products that try to remove these biases, at least the satellite specific biases. And so if you're doing retrospective analysis, you can know the biases moderately okay, at least better than real time. So I don't know, you maybe have better experience with this than I do, but.
And we don't know the effect of the biases, and that would be a good tool to study. I mean, the effect of the actual uncertainty of the existing methods for estimating the biases, you know. Anyway, so then concerning other people using the data, say if I am to use your data, then it would be a lot of work for building the interface because say for Gypsy, it takes raw Rhinex data. And so I would I would say something opposite to what Victoria suggested. I would say, okay, generate Rhinex data for me, you know, observation Rhinex data.
Well,
which
we
would
do
be
actually, we have .obs file as well. So Sergey, I will send you Rhinex data specially. So.
No, I'm just kidding. Yeah, probably it would be easier for me to adjust. I mean, if I have figure out time to do this, then it would be easier for me to adjust the interface to your data. Okay. Yeah, I basically it's not so much a requirement, but yeah, I would prefer Ranix data. And say for vertical profiles, we use SAO. Instead, we use SAO data, kind of. And then I had a question about your Kalman filter. You said that it's extended Kalman filter, which may mean a lot of stuff. So do you really update the covariance matrix in your Kalman filter?
We do.
Or...
So we produce an analysis state and covariance.
Okay, so the covariance, you start with this Gaussian covariance and then it evolves into something.
That's right.
Okay. Okay, and does it look interesting? How it evolves? Does it show?
Yeah.
Okay, go ahead.
Oh yeah, I think it's very interesting, and there's so Mazda is built from IDA, but with much changed, and the way the covariance cycling, we've specifically changed the way the covariance cycling is done, and because of that, we get far more intuitive and nice results with our covariance than IDA does, at least in our implementation of it. So.
Okay, thank you. I'm done with my questions.
Thank you, Sergey.
Okay, we're a little bit over the hour, but thank you for a very awesome talk and a really great discussion at the very end. If anyone else has any questions, they can reach out to Joe, I guess through email, if it's publicly available. Yep, perfect.
Yeah, please do.
All right,
okay.
Great. Thanks very much, and thanks for coming to our last GeoDAWG seminar of the season. We'll see you again after a very fun summer conference session.
All right, thanks everyone. Bye.
Bye everyone.